Okay. All right, everybody. Good to have you back. Let's get started. So this is day 2 of graphs of exponential functions. In Edmentum, it's called exponential relationships, but what we mean is exponential functions. Day 2. So we're going to finish what we started yesterday, and then we should be ready to do the mastery test after we have all of today's info. A couple announcements. Today we're going to be continuing Unit 5, what we started yesterday. Then the schedule for this month might be a little confusing, so I have a calendar I want to show you in just a moment. But next week, we're not going to have class on the 12th through the 13th. So that's Wednesday and Thursday of next week. And then again, no class on Monday, the 17th. Next week, we're doing achievement chats. So you should be scheduling that with your regular independent study teacher. And that's why there's no class on the 12th and 13th. The 17th is Dr. Martin Luther King day. So we're not going to have school then. Unit 5, I'm going to have completed on Thursday, the 20th. So it seems like plenty of time, but honestly, because of all these days we're missing, it's not that much time. So make sure that if you missed yesterday, this is for all of you. If you missed yesterday, to watch yesterday's video and then try doing the homework assignment. It's only 4 questions. And then today, I want you to follow along and do your best and just get caught up on whatever you can today for yesterday and today's work. All right, and we're gonna skip that last announcement for now. Here's a calendar for you to see what that looks like. So here's today, the 5th, Wednesday. So we're gonna be finishing this lesson today. Tomorrow we'll be starting lesson 2 in unit 5, and then Monday, lesson 3, and so forth. We'll be testing right here on the 20th. And then we'll be starting unit 6 the following week on the 24th. So that's like part B. Math 1B starts right here. So if you're still finishing old work, that's okay. But don't put off the new stuff we're doing right now today. Stay current on that and slowly chip away at the old stuff. And then you can still finish old stuff even after this date, but the sooner the better. So don't put it off. And if you ever want to come work with me extra, you can, or Brandon, our tutor, to get help and get caught up on anything in math class. Any questions or concerns on the schedule? All right, let's get started. So we're going to pick up where we left off yesterday. Yesterday, we were going on Desmos at the same time as the video call. So I'd like everyone to do this with me now. Open up a new tab. Keep your video call like on, but open up a new tab for desmos.com. And we're going to enter these 2 functions into desmos.com so we can graph them both. We're going to be comparing the parent graph, the 2 to the x. Here's how we say that out loud. 2 to the x power. Victor. This is our parent graph. It's kind of like the most basic, original, starting exponential function we can have.
Josiah,
Anthony, yes.
what days do we have? Is there no school?
Yeah. Okay, let's go back to that real quick. So here's the days with no school, Anthony, and everybody. I've got some writing in the way there, but here's today, the 5th. So it's next week on the 12th, and the 13th, and technically the 14th, but that's a Friday, so we wouldn't have class then anyways. These 3 days next week are achievement chats. So you should be setting those up with your teacher, your independent study teacher. It's basically like a parent student teacher conference. And then on the 17th, there's no school for Martin Luther King Jr. And then yesterday, today, tomorrow, all these white days, we want to make sure we're in class, doing your best, staying current, do the homework every day. Even if you don't pass it, just try it at least. So that way, when we get to the 19th and the 20th, we'll be ready to go, take our test, be all done with Unit 5. Does that help, Anthony? Does that answer the question or no? All right, I don't hear you. Just in case you, so you know, I'm not hearing you. Any other
Hello?
questions?
Hello?
Oh, now I hear you, Anthony. Go ahead.
Oh yeah, yeah, it worked. It helped. Thank you.
And you know what, folks? I don't think I actually did email this picture to you, this calendar. So let me just make a note to myself, and I'll email this out to everyone after class today, to students and to parents, so you all know the schedule. Okay. Thanks, Anthony. If there's no other questions, let's jump back into exponential functions. Okay, so please do this, everybody. Open up Desmos. I want you to do this on your own as well as me doing it. So that way you're getting practice using Desmos and typing in the functions. So both of these here, y is equal to 2 to the x and y is equal to negative 2 to the x. Don't use a parentheses, just make it negative and then 2 to the x power. I want to compare these two. And while we're doing it, let's ask these questions to yourself. Is the shape of the graph the same or different? So we're looking at two graphs at this on the same picture. And then what is the y-intercept of each function? How does that change when we make it negative? I'll leave this up for a moment, and I want you all to try it on your own, and then I'm going to pull up Desmos as kind of a model in case you need help with that. If you need help typing in the functions, making the exponents, please let me know. You can chat me or you can just ask with your mic. Y is equal to 2 to the x and negative 2 to the x. When you type in your new tab, just go to desmos.com, click on graphing calculator right in the middle, and then you'll have a screen that looks like this. Click back to the video call to see what it looks like. Basically a blank graph. On the left side, we've got space where we can type in functions, equations. So we gotta type in y equals 2, and then to make it to the x power, the exponent, we need to access this little keyboard function on the bottom left corner of the Desmos screen. Show keyboard. And you want to use the A to the B button on the left side of those choices. And that is going to shift up the cursor to type in exponents. So now I can type in x for the x power, and then there it is in red. So those of you who were here yesterday, we did this a lot, right? So we've seen this graph a lot and this function a lot, the 2 to the x. Now I want to also on top of it graph the negative version. So to do that, click below your original and you can type in another new function and keep the old red one there as well. So y equals negative 2 to the x. All right, and then let's zoom out and you can click and drag the graph screen. So I have it graphed on mine. I'm going to check the question in the chat. Oh, nice. Anaya noted that the negative curves up. I'm sorry, the positive curves up and the negative one is curving down. Correct. Thank you for pointing that out. That's what I was hoping you would see. Anaya, thanks for pointing that out. Um, all of our positive graphs that we graphed yesterday will look kind of like the red one. They're all going to be curving up from left to right. And if we make a negative, it curves down from left to right. Now, check out the y-intercepts with me. Remember, the y-intercept is where your function line, the red or blue, where is that crossing on the y-axis? So for the red one, the positive, the y-intercept is at 0, 1. When we make a function negative, like our blue, that changes it to a y-intercept at negative 1. I'm going to go back to the presentation. So come back with me to the video call screen. We did a little bit of this yesterday, but I was a little rushed at the end. So I want to do this again with you all now. So let's talk about end behavior of our exponential functions. End behavior. So you're going to have some questions like this on the mastery test today and on the big test later. End behavior. Basically, what this means is it's describing what the function is approaching, what number the function is approaching towards the left and towards the right. So just for a quick example, what number is it approaching as we go leftwards? And what number is it approaching as we go rightwards? And for exponentials, we're going to be using the infinity idea, which means it goes on forever. So all of our exponentials will have infinity on one of the sides. So let's look at some concrete examples. We're looking for what number the function approaches going leftwards and going rightwards. Okay, so we did this one, I think, yesterday, but let's do it again as a group. This is the function that we've been using a lot. Y is equal to 2 to the x, so it's the one you graphed already. Now, to look at the end behavior, we're looking, pretend you were a little like person walking to the left. So what happens as our little person is, or a ball is rolling leftwards? How high is this blue line reaching? As x goes to negative infinity, as x goes left, same thing as saying goes to negative infinity. What is y doing? Y goes to 0. Why do we say it's going to 0? Because this blue line, I'm going to kind of highlight it, color it. As we go leftwards, it's getting lower and lower and lower. It's getting close to 0, but it actually never reaches 0. It's just getting closer and closer and closer each time. And interestingly, it never reaches 0, which is kind of cool. So here's how we can say that. I'm going to box it on the top again. As x goes to negative infinity, or you could say as x goes leftwards, y is going to 0. And now we got to play the same game on the right side. So as x goes rightwards, now our little person is climbing the hill rightwards. So as x goes to infinity, gets bigger and bigger and bigger, what is the y doing? Well, here y is actually going to infinity also. It's getting higher and higher and higher. And it never stops. So the end behavior for rightwards, as x goes to infinity, y goes to infinity. And we need to be prepared to talk about end behavior using just straight up words or using symbols like this. So like with my arrows. So how we would say this with words is I'll write it out like I did yesterday as X goes to infinity. Sorry about that. As X goes to infinity, Y goes to infinity. Let's look at another example. I did this with one student yesterday, but everyone else had left. So here's a new one. This function is y equals 2 to the x plus 3. So this function is the same exact shape as the last one we just did. However, it's just been pushed up 3 units. So instead of approaching 0, can anyone tell me, as best you can, what does it look like this orange line is approaching as we go leftwards? What's the height of it? You can tell me in the chat or with your mic. Anyone want to take a guess at this? Okay, see someone in the chat. Yeah, very good, Anaya. Thank you. As x, and we started the same way. As x goes leftwards, as x goes to negative infinity, y is going to 3, positive 3. Or y approaches 3. I'm going to add that in below here. You could also say y approaches 3. Same thing. And on the right, as x goes to positive infinity, y is just increasing forever. It's not approaching a certain height and stopping like it is on the left, is it? So we say y goes to infinity. As x is increasing, y is increasing, and it never stops. Okay, it sounds like a lot of people dropped out of the call. Who is still here? Okay. I'll leave this up for a moment if you are still copying down or if you want to take a picture of it. I want to look at one more end behavior example, and then I want to move on to some newer stuff for today. All right, so here's our next example for end behavior. Okay, hopefully you recognize this from what we did first today. This is the graph of y is equal to negative 2 to the x. And like Anaya pointed out, it's curving downwards. So that's our clue that it was a negative exponential. Just the fact that it's starting off looking flat, and as you move to the right, it's curving down. So let's talk about end behavior. As x goes left, or as x approaches negative infinity, what's happening with y? Was y approaching? What is y getting close to? What does it look like? What height does it look like the red line is approaching or getting close to? Can anyone take a guess at this for me? Chat or with your mic.
I'm pretty sure that the way the line is curving, it looks like it's going farther away.
Totally. Yes. Levi, thank you. Stay on the line with me. It's continuing to go farther away. Let me add an arrow here to signify that it's like continuing on the left. But what is the height, Levi? So like here, let me add in our little person. It could be for me. It's a little helpful. I hope it's not too bad for everyone else. Here's our person, and he is walking leftwards. So as this person is continuing down the line, are they getting much higher, or are they approaching kind of a cap or limit where it's stuck at height wise? Like for instance, let me ask another question. Does it look like this person is going to reach up to 2, up to this dash line, based on what we can
I don't think
see?
so.
I covered you.
I,
My bad.
oh, so I honestly can't exactly tell,
Okay.
but I think it's probably going to be under the line just because the way that the line is, it doesn't look like it's going to move up anymore so that the person can meet directly where the 2 is.
Exact. Great observation. Thank you. Thank you, Levi. Exactly. You're right. We don't actually know what's beyond the white edge of the picture, right? But based on what we can see, it looks like our line is basically kind of bottoming out or getting capped off, like a wall, kind of right here at at that point or at that level. And what is that level? Well, look to the right, and that level is 0. So how we would say this is back down below, as x is going left, as our little person is walking left, y is going to 0. Just like, I'm going to go back real quick, just like the first example, right here. This was the first one from today and yesterday. As x is going left, our line is approaching 0 and capped off there. It's not going to cross over. I saw someone in the chat. Let me go back to the negative example. Here we go. So where it looks like it's almost going straight left to right, for exponentials, it's not actually crossing that boundary. It's kind of like a cap or a wall keeping us from going past it. So right here, this is our wall for this one. Now let's talk about the right end behavior. So go now, if the little person changed directions, here he is, but he's going rightwards. Okay, what's happening with him now? As x approaches positive infinity, what's happening with y? Y is also going down, 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 and it never stops going lower. Assuming that our picture continues like this forever, it's never going to stop. So we say y is going to negative infinity. Notice that for all these examples, we always start it with like as x goes to negative infinity, y does what? As x goes to positive infinity, y does what? So it's kind of like as we go leftward, what's the height reaching? Is it going to infinity, forever up, or is it being capped off at 0 like this picture? As x goes to the right, is y being capped off, or is it going down, down, down to negative infinity forever? With exponentials, one side is always curved, remember? So one of these is going to be y going to either up infinity or negative infinity forever. I'll stay on this page if anyone is still copying or writing, and then we're going to move on in just 10 seconds. If there's any questions, please interrupt and let me know. I'd love to hear from you for anything to clarify. Even if it's from an older page, we can go back to it. Okay, let's look at some new stuff. Okay, let's kind of pause for a second and go over the main takeaways that we have so far. And this is including yesterday's work and today's so far. So here's our generic version of a exponential function. Okay. Um, for example, I'm going to put up here as an example. We've been using a lot this function, y is equal to 2 to the x. So below, in our generic version, instead of having a 2 there, I'm going to put b because any number could be that b value, right? And any number could be the c value. We've done examples yesterday where we added and subtracted +3, +5, -10, something like that. So our main takeaway so far from what we've seen would be this. Um, we always have x as an exponent. So let's add that in here. X is always the exponent, the power. How about the b? Let's focus on that b. If b is positive, then it curves up. It has this shape with a cap going to the left. Today we looked at a negative b. If b is negative, then it starts off flat looking like this, but then curves down dramatically. Now remember, the b could be any number. It doesn't have to be just 2. That's the one that we use a lot though because it's our parent graph. It's our most simple, most foundational, like starting point for any exponentials, 2 to the x. And then yesterday we looked at adding a number or subtracting a number like this. So the plus c pushes the graph up or pulls it down that number of units. C units. I'm going to separate these. Okay, now yesterday we talked about the zero power because we have to do, I'm going to show you this really quick. Okay, so we did a problem like this yesterday where we were given the function y is equal to 2 to the x, not 1/2, but 2. And to graph it, we made a table and just plugged in values 0, 1, 2, 3, and so on for x. And we didn't talk about why anything to the 0 power is always 1, and we didn't talk about how to do negative exponents either. I want to have a quick side lesson with you and review this with you on these two questions. Why is anything to the 0 power always equal to 1? And then how do we calculate negative exponents? How do we deal with those? Yesterday, I told you to basically just trust me on anything to the 0 power is 1. I want to show you why that is, though. So let's do a quick example for this to answer these two questions.
Josiah,
Levi, please.
okay if for the question, why is anything to the 0 power equal to 1?
Yeah.
I think it kind of stands for like the rule that goes for multiplication where anything times 1 is equal to that number.
Totally. Yeah. I love what, here, let me go to a blank screen. Levi's saying anything times 1, an earlier rule that we learned, right? Like, let's say 5 times 1, still 5. And why is that? Because multiplying 1 doesn't change anything. It is very similar. So for instance, we're dealing with exponents now, the exponent world. we raise something to the 0 power. 5 to the 0 power. Let's do another one. 2 to the 0 power, still 1. 10 to the 0 power, still 1. And it seems weird. And you're right. It's kind of like this foundational idea that we learned earlier, that anything times 1 is just itself, doesn't change it. What Levi or anyone, please feel welcome to answer this question for me. We talked yesterday about exponents and what they mean. I want to make a short list here of some powers of 2. Let's do 2 to the 1, 2 to the 2 power, 2 to the 3 power, 2 to the 4 power. We'll stop there. We could keep going, right? We could do 2 to the 5, and this list goes on forever. Um, anyone, can you tell me what is 2 to the 1 power? If I wanted to simplify this, 2 to the first power. Something in the chat. 2, Savannah, thank you. And Savannah or anyone, this is open for everyone. What is 2 to the second? And then I want to ask you, how do you figure it out? What does the second power mean? Savannah said 4, correct. Can you help me with the second question of how did you figure that out? Or like, what does the second power mean? How do we know how to take a power of something? We talked about this yesterday for folks who were with me yesterday.
It's like multiplication. You take the what's it called? You take 2 and you add it 3 times, and you would get 6. Or you take 2 and you double it by 4, and then you get 8.
Yes, and exactly. The symbol of the power, the exponent, is telling us how many times. Levi, you don't mean add though. You mean
I mean multiply.
multiply. Yes, exactly. So
Like,
2 to the third, technically this means 2 times 2 times 2. And when you multiply all 3 of those 2's together, that's 2 times 2 is 4. 4 times 2 is 8. 2 to the fourth power would be 4 2's all stacked up, multiplied together. Very good. So there is a parallel between like how we learned how to multiply earlier in life and now to use exponents, right? One is when we're multiplying, that means we're adding it a bunch of times. Exponents means we're multiplying it to itself a bunch of times. So for 2 to the fourth, 2 times 2, 4. 4 times 2 is 8. 8 times 2 is 16. So here's the first 4 powers of 2. 2, 4, 8, 16. Okay, now I want to ask you guys all a question about this second row. Our first row is the powers, 2 to the first, 2 to the second. About this row right here, 2, 4, 8, 16. Can you tell me what is the pattern going from 2 to 4, from 4 to 8, and from 8 to 16? Do you see a pattern that can take you from 2 to 4, 4 to 8, 8 to 16, and maybe on to the next one? What would come after 16 right there? It's not an adding pattern. Is there a multiplying pattern that we can use, like a rule or a pattern that gets us from one number to the next, going increasing, going bigger?
I think it's 4.
Okay, are you saying add 4 or multiply 4?
Multiplied 4.
Okay, I love it. Let's test that out. 2 times 4, 4 times 4, 8 times 4. Levi, you're on the right track, but I want you to take that idea of 4. and timesing 4, and we're going to tweak it a little bit. 4's on the right track, but there's another number that does, when we multiply it, gets us from 2 to 4. Then from 4 times the same number gets us to 8. 8 times the same number gets us to 16.
Oh, it's 2.
It's 2. Levi, thank you. There's some stuff in the chat. Savannah, very good. Both of you for noticing that and for speaking on it. It's times 2. So the pattern is basically we're timesing 2 to each like a previous term to get us to the next one. So with that in mind, we could figure out 2 to the 5 without a calculator if we had this list in front of us, because 2 to the 5 would be 2, looking at our pattern below, times 16. So 2 times 16 gets us 32. And if you check it on your calculator, it is. 2 to the 5th power is 32. So every time we move up in a power, like higher power of 2, it's just times another 2. That's my point I wanted you to see. Okay, now my question. With this pattern in mind, what's the pattern going backward in the list? So if we're timesing 2 to go bigger, so let me write that out here. We're multiplying 2 to increase power. What's the pattern to decrease power or go backwards? Meaning 32 to 16, 16 to 8, 8 to 4, 4 to 2. Do we see a pattern going backwards? And it's not multiplying this time, it'll be dividing. Pattern to decrease power. Anyone see that? Can I divide something to 32 and get 16? Divide 16 by the same number and get 8. Divide 8 and get 4. Divide 4 and get 2. What's the pattern to go the other direction? Let me.
Dividing.
Oh, who was that?
Anaya.
Anaya. Thank you. Yes. The pattern to go backwards, because one way, the first way is multiply 2, then it stands to reason that the pattern backwards should be divide by 2. Let me put that in my little list here, and let's check it out. Test it out and see if it works. 32 divided by 2 does get me 16. 16 divided by 2 gets me 8. 8 divided by 2 gets me 4, and so forth. So now we finally get to the 0 power and the negative exponents. Look up at the list with me again at the very top where we started. The powers, 2 to the 1, 2 to the 0, 2 to the 2. What should come on the other side? What should come on the left side of the screen? Looking at the exponents, they're decreasing, right? 5, 4, 3, 2, 1. So the next integer, next whole number exponent would be 2 to the 0. And while we're at it, let's put some negatives in there. After 0 would come 2 to the negative 1, 2 to the negative 2, and 2 to the negative 3. And I'm going to stop it there because it could go on forever. Next would be 2 to the negative 4. So how do we find 2 to the 0? Let's use our patterns that we've found. The pattern is divide by 2. So looking above, looking at 2 to the 1, well, that is 2. Savannah pointed out for us. 2 divided by 2, what is that? That is 1. Remember that other rule we use a lot, anything divided by itself is 1. That's why anything to the 0 power is always 1. because the zero power is the base divided by itself, going backward in this pattern. It's 2 divided by 2, 1. Then how about 2 to the negative 1? Well, that would be this number, the 1 we just had recently, divide by 2. That's 1 over 2. Put that right here. What's 1/2 divided by 2? 1/4. 1/4 divided by 2. 1/8. I'm going to change my color to purple quick. So focusing now just at the top, the powers, and then like what their values are. I'm going to circle or box those right now. On the top, we've got the powers of 2, and then below those, we have their actual numbers, their value, right? There's actually some symmetry going on here, which is kind of nice. The negative exponents, 1/2, 1/4, 1/8, those are mirrored on the right side with their whole number equivalents. So we see 1/2 and 2, 1/4 and 4, 1/8 and 8. And if we had to show 2 to the negative 4, that would be 1/16. 2 to the negative 5, 1 over 32. So if you can do the positive powers, the negative powers are just 1 over that its match on the positive side. How do we sum this up? Negative exponents are 1 over 2 to that power. Negative exponents is a symbol telling us you're still kind of multiplying the base 1 time or 2 times or 3 times, but it's in a fraction, 1 over 2 to that power. And you know what? The pattern still works. So the multiplying pattern gets us larger powers. The dividing pattern gets us smaller powers. So like look at 2 to the negative 2 with me. 1/4, if I use my multiplying pattern to increase, 1/4 times 2, well, that's 2 over 4. 2 over 4 is 1/2. So it works. 1/4 times 2 is a half. 1/2 times 2 is 1. 2 over 2 is 1. So to increase powers, we're basically multiplying the base, like we've talked about. And then to decrease power, and that's what gets us down into the power of 0 and negatives and so forth, then we're basically just dividing by 2 for every power that we have. Let's look at an example now to use this information, to use like our negative powers. Yesterday we did an example, but we didn't do the negatives. Now we can do that because we know how to like deal with a negative exponent. Okay, our final like I guess case that may come up for an exponential function is this: when b is between 0 and 1. And here's what that looks like in symbols. B is greater than 0, but it's less than 1. It's between 0 and 1. Greater than 0, but it's less than 1. And here's a few examples of what those will look like. This is, instead of 2 to the x power, I've got a half, 1 over 2 to the x, or 3 over 4 to the x, or 2 over 7 to the x. These are just 3 examples. There's, an infinite number that we could come up with, different fractions. So what happens when we graph an exponential when it's a fraction base instead of, a whole number like we've used so far? Let's graph the parent function for this. just like we did yesterday, y is equal to 1/2 to the x power. So evaluate the function for each x value in the table, and then we'll plot the points on the graph. Now, this time I expanded our table to put in negative values for x, which will basically be negative exponents. And then we'll graph those to see what this looks like. Now, this is not going to be the same shape as our negative 2 to the x like we did earlier. This will be a little different. Let's start with the 0 and maybe do the positives, and then we're going to back up and do the negative exponents. So we'll take our function, y is equal to the 1/2 to the x power, but instead of the x, we're going to plug in 0 for this part of the table. Anything to the 0 power is the number 1. So we plugged in 0, we got out 1. Remember that rule. Anything to the 0 power is 1. It's always a good place to start. And then plugging in 1. This is another good one to do next. The first power. Remember, the first power means you multiply the base to itself just one time, like this. 1/2, and we're done because there's only one of them. So we plugged in 1, we got out 1/2. Now plug in 2 for x. So the second power. So 1/2 to the second power. So using our knowledge about exponents, this means 1/2 times itself 2 times. So we have 1/4. Okay, let's do the next two. The third power, so that's 1/2 times itself 3 times. Now remember, the top is 1, 1, 1. That's just a 1. 2 times 2 times 2 gets us 8. 2 times 2 is 4, and then 4 times 2 is 8. So just check out what's happening with these outputs. They're getting, they're getting smaller and smaller and smaller each time. 1, 1/2, 1/4, 1/8. Let's do our last one. 1/2 to the 4th. Shoot. Okay. So using that work we did on the table previously, we know this is just 1/8 divided by 2, 1/16. 1/2 times itself 4 times. And that fits the pattern we're seeing in the y portion of the table, the output. 1, 1/2, 1/4, 1/8, 1/16. Now let's look at the negative exponents. So we plug in -1. So I'm going to go back real quick to this page. So notice that when we're taking a negative exponent of a whole number like 2, it basically flipped it and made a fraction. So 1/2 to the 1 and 1/2 to the 2, 1/2 to the 3. So that flipping is another way to think about negative exponents. You take whatever the base is, you raise it to that power, and you flip it. So if we apply that here, then if we flip the fraction to 1/2, that becomes 2/1 to the first power. And that's just 2. Same thing for plugging in a -2. Flip the fraction, so now it's 2/1, that's better for us, and it's being raised to the second power. So that's 4/1, or just 4. And also notice that symmetry is happening. So if we look at our table, we already did the fraction part, the 1/2, 1/4, 1/8. that symmetry is going to happen for the whole number part above. So the next number in our list should be straight up 8, whole number 8. That's just using the pattern. But what about working it out? 1/2 to the negative 3 power. Flip the fraction. And then 2 to the third we know is 8. So now we have enough points that we can plot this and get an idea of what it looks like. So remember, we're looking at the x and the y. So starting from the top, we've got negative 3, comma 8. So negative 3 and then up 8. I'll label it. Negative 2, comma 4. Negative 1, comma 2. The height is being cut in half each time. And 0, 1. There's that same y-intercept as we saw before. And then now we're getting into the fractions. So here we'll just do our best. 1 comma half. So that's over 1 up a half. So that'll be like right in between 0 and 1. And then 2 comma a fourth. Again, just do your best. Let's cut this distance in half from 0 up to a half. So that's like right here. And then 3 and an eighth. I mean, we're getting really small, right? And then 4 and a 16th. And we're going to get to a point where we can't really measure this. It's just estimating. And actually, that's why these are never actually reaching the line. It's never actually a straight line, horizontal, because it's just being cut in half each time. So it's getting closer and closer and closer to the x-axis right here, but it never reaches it because it's being cut in half and cut in half and cut in half, and it's getting closer and closer and closer by a little bit, by a fractions, but it's never going to reach it, which is kind of cool. It looks flat, but it's just getting closer and closer. So here's our shape for exponentials that have a fraction between 0 and 1. It's a decreasing function. It starts off really high, and as you move right, it's curving downward and then kind of bottoms out against its barrier, its wall. Okay, I see it's almost 12 already. I had one more page to kind of sum up what we've seen. So it's the same as before, but also if B is between 0 and 1, like for instance, if it's a half or a fourth, or if it's 2/5 or any fraction that doesn't reach 1, 2/5, maybe 3/7, anything like that, then our graph has this shape. It's a decreasing function. The first examples we've been working with, B was always like a whole number bigger than 1. So if B is greater than 1, like for example 2 or 3 or 5 or 100 or anything bigger than 1, then it's a reverse image of the decreasing. It's a growth function. It starts off low, flat looking, and then curves up. And then today we also looked at what if it's negative? So if b is a negative number, then this is another like reversal of the shape. It looks flat and then it curves down. So this you could say is also decreasing, but it's a sharp, quick downward going into towards infinity, negative infinity. This one's the growth function is going up to positive infinity. The decreasing function in the middle isn't going to negative infinity. It's bottoming out against its like wall. It's getting flat against its barrier. So that's a little different. Okay. Now, next, I just had some questions from the mastery test I wanted to look at with you, but it's 12, so I've got to let you go. So, sorry we didn't get to those. Here is the homework from yesterday and for today. So we have covered everything from that first lesson. So yesterday's homework, and this is still required for everybody, page 11 from the first tutorial. Only page 11. Do page 11 and then hit submit so I can see your guys' work. 4 questions only. And then for today, the mastery test for graphs of exponential relationships. So we should have both of those done. 4 questions on page 11 and the mastery test. Tomorrow we're going to start the second lesson. I want to build in time in the beginning to go over any questions you guys have from these 2 homeworks, okay?